the first case is when b squared minus 4ac is positive. And in that case, we'll get two real values of lambda. So we've got our b squared minus 4ac is greater than 0. And as an example, let's take y double prime plus 4y prime plus 4y, beg your pardon, plus 3y is equal to 0. So that is an example. Well, let's work out what the roots are. So we'll find the characteristic equation. One way of doing it, of course, is just to remember, well, okay, a is 1, b is 4, c is 3, and just write it down. But in fact, I prefer deriving it again. I do find that sometimes you remember a formula, sometimes you don't always remember it quite right. But if you can remember how to derive it, it's a much more reliable way of solving these problems. So the way to derive it again is to remember that what we're doing is we're trying y is e to the lambda x. So y prime gives you a lambda e to the lambda x, and y double prime is lambda squared e to the lambda x. And so putting y double prime in here gives you a lambda squared, and we've got a 4 lambda, and we've got a 3, all multiplied by e to the lambda x is 0. And this e to the lambda x, we've already decided, is never equal to 0, so we can divide by it. There's our characteristic equation, or auxiliary equation, lambda squared plus 4 lambda plus 3 equals 0. You can either factor it, you can spot how to factor it, or if you can't spot how to factor it, we can use the quadratic formula. So the quadratic formula is lambda is minus 4 plus or minus the square root, so it's b squared, b is 4, so it's 16, minus 4ac, so it's 4 times 1 times 3, all divided by 2a. So a is 1, so that's 2. 16 minus 12 is 4. Square root of 4 is 2. So that's minus 4 plus or minus 2, all divided by 2. So if it's minus 4 plus 2, that's minus 2. Divided by 2, so lambda 1 is minus 1. And lambda 2 is minus 4 minus 2, minus 6 divided by 2, so that's minus 3. So we get our general solution is y is c1 e to the lambda 1x, that's e to the minus x, plus c2 e to the minus 3x. Okay, so that is an example of the case where we have two real distinct roots. The next, well, I can it might be of interest, of course, to plot what these look like, and I will do some examples of these plots at the end of this podcast. So the second possibility is that this b squared minus 4ac here could be equal to 0. Remember the three cases, it's either positive, equal to 0, or negative. So if we take the second case, I'm going to make it equal to 0 now. And an example where it's equal to 0 is where that 3 is a 4. And in that case, everything works the same. That 3 in here becomes a 4, right? So we try y is e to the lambda x, y prime is lambda e to the lambda x, and so on. Put the y double prime is a lambda squared. The 4y prime, so that's 4 lambda. The 4y, so that's 4 equals 0. And now, if we use our quadratic formula, we get lambda is minus 4 plus or minus square root of b squared, so that's 16 minus 4 times 1 times 4. So here it becomes minus 16. So this is minus 4 plus or minus 4, plus or minus 0 over 2. So we only get one value of lambda in this case, which is minus 2, but it is repeated. So this is the case where we've got real roots of our characteristic equation, real values of lambda, but instead of having 2, we've only got 1. So we have one solution. And that is y is c1 e to the minus 2x. Okay? But one thing we know about second order differential equations is they should have two solutions, and not just two solutions. They should have two independent solutions, two solutions that are different from each other. This method has only given us one. So how can we find a second solution? Well, there are two ways of doing it. One is to ask somebody, and they'll tell you what the second solution is. And the other way is to figure it out yourself. So I'm going to adopt the figure it out yourself method. And I'll use a technique called reduction of order. And that is a technique for which there is another podcast in this series. So you can go and listen in more detail about reduction of order. But the way it works is if it works in the case where you've got, say, a second order equation and you're told what one of the solutions is. And reduction of order allows you to take this second order equation and bring it down in order down to a first order equation, which is something you can solve. And in that way get a second solution to this equation. So let me proceed with the method of reduction of order based on this one solution that we have. So we'll use reduction of order to find a second solution. Okay, so the way that works is we take as our guess for y an unknown function times this solution. So we'll try y is u of x. So u of x is an unknown function times that solution. And I don't have to put that c1 in there because that c1 can be absorbed into the u. So it's just y times e to the minus 2x. Sorry, y is equal to u of x times e to the minus 2x. All right, and the idea is somehow this is going to help us solve the problem. So let's pop that into the differential equation and see if it tells us something about u. So we need y prime. So it's the derivative of this. It's a product of two functions here, u times e to the minus 2x. The derivative of a product, we use the product rule. So that will be u prime times e to the minus 2x plus u times the derivative of e to the minus 2x, which is minus 2 e to the minus 2x. Okay, that's y prime. We need y double prime as well. Well, we've got two products. We've got u prime times e to the minus 2x. We'll differentiate that. We get a u double prime e to the minus 2x plus u prime times minus 2 e to the minus 2x. That's differentiating. First, we differentiate the u prime, which gives us u double prime. And second, we differentiate the e to the minus 2x, which gives us the minus 2 e to the minus 2x. So that's this first pair. Now we have to do the same thing with the second pair. So we differentiate u, we get u prime. So actually u prime times e to the minus 2 e to the minus 2x. So in fact, it's another one of these. Okay? And then we have the u times the derivative of the stuff that's in the brackets. It's a minus 2, and another minus 2 comes down that makes it 4 e to the minus 2x. All right, there's y double prime. We'll put it in here. Y prime, we'll put in there, and y, we'll put it in at the end. So we'll do that. So we've got, well, everything is multiplied by e to the minus 2x. So I can just take a factor of e to the minus 2x out the front, and then we've got u double prime, and then it is 2 and minus 2, so 2 times minus 2 u prime, so it is minus 4 u prime. And then we've got plus 4 times u. Okay, that is the y double prime. And now we want 4y prime. So we need 4 of these. So we want 4 u primes and 4 of these. So this is minus 2 times u. So 4 of those is minus 8 times u. And now we want 4 y's. So it is 4 times u times e to the minus 2x, so it's plus 4u. The e to the minus 2x's have come out in front, and that's now equal to 0. So e to the minus 2x is never 0, so we don't have to worry about that. What we've got in here, we can simplify. So the first bit we've got is u double prime. How many u primes do we have? Well, there's minus 4 of them here, and there's plus 4 of them there. So they cancel. And how many u's do we have? We've got plus 4 of them there, we've got minus 8 of them there, and we've got plus 4 of them there. So they add up to 0 as well. So our equation that we're trying to solve is now u double prime equals 0. So the point of reduction of order is it's supposed to take the equation you're trying to solve and the solution that you already know, e to the minus 2x, and give you an equation for u that is in some way simpler than what you started with. The way that it would normally work is you'd have a u double prime and a u prime at this point, and you would define a new variable v, which would be equal to u prime. You'd end up with a first order equation for v. Here, in fact, it's even simpler. The equation we're trying to solve is u double prime equals 0. So the second derivative of a function is equal to 0. That means the first derivative is a constant. We integrate this equation once. We get u prime is a constant, which I'm going to call C2 for a reason that will become clear in a moment. Now we integrate that one again. We're integrating a constant. So when we integrate a constant, we get our function u, which is C2 times x plus C1. You integrate this constant, it becomes a constant times x, and you have a constant of integration. Okay, so our solution for this equation, u double prime equals 0, is actually u is a straight line. U is C2x plus C1. But that wasn't what we were trying to solve. We were trying to find y. Y was equal to u times e to the minus 2x. So y, which is the general solution of that equation, is going to be C2x plus C1 e to the minus 2x. And that's the general solution for this differential equation. And notice that it includes the solution that we had before. Before we had y is equal to any constant times e to the minus 2x, and that's there. It's the C1 e to the minus 2x. It's included in this general solution. The new part is a constant times x times e to the minus 2x. And that is in general what happens in the case where you have b squared minus 4ac equals 0. That is, you have real repeated roots. One of these solutions is e to the root times x, and the other solution is x times e to that root times x. So we have now the general solution for that problem.